Earth, a 4.5 billion year old planet, still evolving. As continents shift and clash, volcanoes erupt, glaciers grow and recede. The Earth's crust is carved in numerous and fascinating ways, leaving a trail of geological mysteries behind. In this episode, Loch Ness in the Highlands of Scotland is explored. It holds more water than any other lake in Britain, with a bedrock containing some of the oldest rocks on the planet. Set in a landscape that was once part of America, Loch Ness is a lake with an enduring myth, the Loch Ness Monster. A team of scientists investigate how Loch Ness was made. The clues they uncover also provide a window into the formation of the Earth itself. Deep, dark, and full of mystery. This is Loch Ness in the Highlands of Scotland. For 1,000 years, there have been claims that this vast lake hides a strange and terrible secret, the fabled Loch Ness Monster. A mythical beast, suggested by some as a descendant of the dinosaurs which once roamed this part of Scotland. Loch Ness would be the perfect hiding place for a prehistoric monster. At 23 miles long and a mile wide, this vast freshwater lake covers the same area as New York's Manhattan Island, and it's more than 700 feet deep. But the monster is not the only mystery that surrounds Loch Ness. In the hills above the loch, there is a type of rock whose origin baffled scientists for years. It's a sandstone, and it's the start of the investigation into how Loch Ness was made.
It's known as the Old Red Sandstone, and it's given that name because it's red and it's a sandstone. And it's called old because it's about 350 million years old.
The Old Red Sandstone runs down one side of Loch Ness. But the most astonishing fact about these rocks is not their age, but where they come from.
These rocks actually belong to my homeland of North America because these rocks originated on the North American continent and then have separated from North America. But in many ways, this is almost a little bit of home for me here in Scotland.
But how do geologists know that this Old Red Sandstone comes from 3,000 miles away, on the other side of the Atlantic Ocean?
These rocks are identical in age and character to the rocks that actually form the Catskill Mountains. And so this part of Scotland belonged to northeastern North America.
For more than 1,000 years, Old Red Sandstone has been used for building castles in this part of Scotland. But it's also been quarried in the US and used for brownstone buildings in New York City. Under the microscope, rocks from both continents have an identical crystal structure, and chemical analysis has also proved that they're exactly the same age. But how did part of America end up on the shores of Loch Ness? To answer this crucial question, the investigation must go much further back in time to look for evidence in the ancient bedrock of northern Scotland. It's here that the story of Loch Ness begins. The trail starts north of Loch Ness, where the bedrock comes to the surface. This landscape is full of the extraordinary mysteries of an unimaginably ancient past. It's made of a type of rock called Lewisian gneiss. Recent drilling and blasting for a new road cut have exposed evidence which uncovers an amazing chapter in Earth's history. The long straight lines are the drill holes left in the rock face. Modern radioisotope dating has given geologists the first clue to understanding the origin and formation of these rocks.
These rocks are very special to geologists. They're some of the very oldest rocks in the world. We see them in very few places. Perhaps a dozen places across the globe contain rocks of this age. Talking about 2.5 to 3 billion years old.
The origin of the gray Lewisian gneiss lies in the first crust that cooled on the surface of the Earth. After its formation 4.5 billion years ago, parts of this crust were mixed together with the earliest sediments, buried, remelted, and forced back up again and again for more than 1 billion years. These extraordinary rocks are the result of that devastating period in our planet's history. And there's more evidence exposed in this road cut, revealing crucial information about the early history of the Loch Ness region.
This exposure contains 3 important pieces of geological jigsaw puzzle. First, we have the grey gneiss, 2.5 to 3 billion years old. Secondly, we have this black igneous material which has been intruded into the area. This is 2 billion years old. And thirdly, we have this pink granitic intrusion that both intrudes the black material and the gneiss, and this is 1.8 billion years old.
This evidence reveals that after the formation of the Lewisian gneiss, much younger rocks were then melted and mixed into the ancient crust. But this process took an incredible length of time.
What we've got here are rocks that record over 1 billion years of Earth history. Now, to put that into perspective, that is almost 1/4 of the age of the Earth recorded in this exposure.
This is the bedrock of Loch Ness. It carries an extraordinary story of a major part of Earth's history. And there are yet more secrets hidden in these rocks.
It looks very much, because of the temperatures and pressures that these rocks were under, that they've been to depths of perhaps 50 miles beneath the Earth's surface in the past. This suggests that these rocks have been to hell and back 2 or 3 occasions over a 1 billion year period.
Geologists now know that the only force powerful enough to produce this extraordinary mix of rocks is plate tectonics. Plate tectonics is the process by which the giant plates of the Earth's crust are driven slowly across the planet's surface by vast convection currents deep in the Earth's hot mantle. In the Loch Ness region, the evidence in the road cut reveals that incredible pressures forced the crust deep down into the Earth, where it was melted, deformed, mixed together, then finally brought back to the surface. After that, for another 1 billion years, this ancient landmass quietly eroded down to a rough, rolling landscape. But this wasn't the green terrain we see now. There was much less oxygen in the Earth's atmosphere than today, and the surface would have looked like a lunar landscape, desolate and sterile. Incredibly, remnants of that billion-year-old landscape are still preserved today. The clues are revealed in another road cut, where the trained eye can draw amazing conclusions from what looks like a jumble of rocks.
At this road cut, we can see Lewisian gneiss, which is between 2.5 and 3 billion years old. But up here, we have something completely different. If I go up to this level and look above it, we have horizontally bedded red sandstones.
This sudden change in rock type helps to unravel the mystery hidden in these ancient formations.
They're believed to have been laid down in a continental environment by rivers. We've got river systems that laid down horizontally bedded sedimentary rocks on an ancient landscape.
So this simple outcrop reveals that even in a world with little oxygen, the ancient bedrock of Scotland was covered in rivers 1 billion years ago. And there's yet another secret hidden here.
There is a junction between these rocks, which are almost 1 billion years old, and the rocks below that are 2.5 to 3 billion years old. This is a major time gap of between 1.5 and 2 billion years.
The time gap revealed here is extraordinary. It shows that after the traumas of their early formation, The rocks of the Loch Ness region went through a period of calm, which lasted more than a third of the age of the Earth. The investigation into how Loch Ness was made has uncovered its first evidence. Identical old red sandstone found on 2 continents proves that Scotland and America were once joined together. Some of the oldest rocks in the world reveal that the bedrock underlying Loch Ness was made during the primeval creation of the Earth's crust. Bedded sandstones lying on the ancient bedrock show that rivers flowed over this landscape 1 billion years ago during a long period of tranquility. But the calm couldn't last forever. A major continental collision was looming, and with it the union between Scotland and England. The investigation into how Loch Ness was made will next uncover the geological structures which would eventually create Loch Ness. The search for evidence begins with a 19th century scientific mystery. In the 1880s, geologists in Scotland were baffled by a sequence of rocks they found north of Loch Ness. Here in a remote hillside lay the problem. A huge mass of very old Lewisian gneiss was lying on top of much younger rocks. But the 19th century geologists had never encountered this before. In their experience, younger rocks always lay on top of older beds. Then, one scientist invented a novel approach to try to solve the puzzle.
A survey geologist back in the Victorian age, 125 years ago, mapped this area, and his name was Henry Cadell. He went back to Edinburgh and he worried about what he'd seen in the field and thought, how do I replicate what I've seen? How does this happen? So he built a model and he attempted then to show, using the model, what it was that he saw in the field.
Cadell's model was simple. He suspected that some force had squeezed the rocks horizontally to make this upside-down sequence, so he built an apparatus containing layers of sand and clay to test his ideas. Professor Underhill is using a replica of Cadell's equipment, filled with alternating layers of black sand and plaster of Paris, to try and duplicate Cadell's experiment. Turning the screw winds the block forward, imitating the horizontal pushing force that Cadell thought was the culprit. As the horizontal force increases, the layers are pushed over each other along a shallow plane, which geologists now call a thrust fault.
And we've got the first thrust appearing. Oh, look at that. Another thrust going in.
The experiment showed Cadell exactly how older layers, the ones on the bottom, are pushed over and on top of the younger layers along the plane of the thrust fault.
There's some beautiful structures in here. There's a thrust fault running through here, which duplicates the white layer. And another one through here, and the final thrust fault, which is at the lowest angle, out here towards the left-hand side. A success in terms of a simple model replicating what we see on the ground. And I can see how Cadell and others, when attempting such things, began to understand what it was that they saw in the field. They could replicate it in a simple, crude model, but replicate it in a very successful manner.
Once Cadell and his colleagues understood the principle of thrust faults, the apparently illogical sequence of the rocks they saw in northwest Scotland began to make sense.
Well, the slope represents a thrust fault. What we have underneath it is a bedded, younger quartzite succession, which is pink. Above it, the grey rock, the rubbly grey hillside we see above, is the Lewisian gneiss again. And the surface in between, which is putting older rock, the grey material, onto the pink rock, the younger material, is the thrust fault, just like in the model that we saw before.
Geologists now know that a thrust fault is the smoking gun that shows where continents have collided. But which continents were colliding to make the thrust faults in Scotland? and how were they involved in making Loch Ness? The scientists' trail now led them to another thrust fault, the Moyne Thrust. The Moyne Thrust is one of the biggest thrust faults on Earth. Running for 120 miles down the northwest of Scotland, it's mostly hidden from view. But Professor Underhill has found one of the rare locations where the thrust can be seen on the surface. This apparently insignificant join between two rock layers is the actual line of the thrust. And it reveals a geological bombshell. The dark layer above the thrust comes from England, but the surprise lies in the yellow limestone below it. Just like the old red sandstone at Loch Ness, this rock comes from North America. This one small piece of evidence has enormous implications for the formation of Loch Ness.
The amazing thing about this contact is that it's the meeting point between two continents. So here we are on a wet Scottish hillside on a Sunday afternoon, and I am touching the contact between effectively America and northwestern Scotland on one hand and England on the other, as was 425 million years ago.
But how did these two ancient continents collide? 450 million years ago, a supercontinent containing North America and Scotland lay deep in the southern hemisphere. At its margin was an ocean wider than the present-day Atlantic. On the other side was England and Europe. But the forces of plate tectonics were slowly pushing the two land masses together.
Well, around 450 million years ago, there was a major ocean where we're standing now. It was called the Iapetus Ocean, and it separated America and northwestern Scotland on one hand from effectively southeastern Scotland and England on the other hand. Now, what happened in the 20 million years after that, that ocean closed and eventually was closed sufficiently that two continents collided into each other.
The collision between America and Europe pushed massive layers of rock over each other, forcing upwards a range of mountains higher than the Himalayas are today. Still firmly attached to America, Scotland and England became fused together. But what did this collision have to do with the making of Loch Ness? The loch itself provides the most fundamental evidence.
The one thing that's quite striking about Loch Ness is that when you look at it, particularly from this perspective, you can see that it runs straight, almost straight as an arrow. And that straightness goes on for about 20 miles. And as a geologist, that tells me that there has to be a control on this topographic straightness because nature doesn't produce things in straight lines. And so there is a structure here that is controlling the overall shape of Loch Ness itself.
This structure is the Great Glen Fault, a major geological fault line formed during the continental collision 425 million years ago. It runs for more than 300 miles right across Scotland, slicing the country in two. Loch Ness exactly follows the line of the Great Glen Fault.
The Great Glen Fault, it's not a thrust fault like the Moyne Thrust where material has been pushed up over. It's not a normal fault where material drops down vertically. It's lateral motion. The Great Glen Fault is Scotland's version of the San Andreas Fault. It's just 400 million years older.
The Great Glen Fault is no longer active, but this giant split in the Earth's crust has been a feature of the Scottish landscape for more than 400 million years. It's the foundation of Loch Ness, and without it, the loch could not exist, nor could the legend of the Loch Ness Monster. The investigation into how Loch Ness was made has uncovered more evidence. The discovery of thrust faults showed geologists what happens when continents collide. Yellow limestone from North America found at the Moyne Thrust proves that America and Scotland crashed into England 450 million years ago. And the shape of Loch Ness reveals the straight line of the underlying Great Glen Fault, formed during that continental collision. After the collision, the forces of plate tectonics drove Scotland south, round the surface of the Earth. Now, the investigation must follow its amazing journey. The next step in the investigation into how Loch Ness was made traces Scotland's journey round the surface of the Earth, driven by the forces of plate tectonics. Understanding what the environment was like in the past gives clues to the location of Loch Ness millions of years ago. So the investigation now moves on to the Jurassic period, 165 million years ago. The trail leads to the Isle of Skye, an island off the west coast of Scotland. At Staffin Bay, there is an incredible piece of evidence which sheds light on this period in Scotland's past. Astonishingly, it lay in plain sight but undiscovered until 1994, when an amateur geologist made an extraordinary find. On the flat, rocky shoreline of this popular beach, he discovered a fossilized footprint of a giant dinosaur. Dr. Anjana Katwa has come to analyze the details of this remarkable evidence.
When you walk across these ledges, it's just an incredible feeling to think that dinosaurs walked on the same ledge that I'm walking on now 165 million years ago. This ledge, we've got this wonderful Megalosaurus footprint. The megalosaur was a 25-foot-high carnivorous dinosaur, quite a formidable predator during Jurassic times.
With some individuals standing as tall as a football goalpost, Megalosaurus was a fearsome monster. But how could something as temporary as a footprint be preserved for 165 million years?
The footprints are so unique. What's happened is that a dinosaur has travelled over a kind of sticky, gooey mud, and their impressions have been left behind. That mud has dried off and it's hardened, and then over time, wind-blown sand has come in and covered that footprint over. And then as further time has developed, we get layers of clay and sand building up over that footprint, and that footprint becomes fossilised over time. Now, over a few million years, erosion occurs and those footprints become exposed for us to see today.
Dr. Katwa is making a plaster cast of one of the footprints, so she will be able to examine it more closely.
We take the casts in order to have a record of the footprints so we can take them back to the lab and have a look at them and understand how this creature used to live.
As she carefully removes the plaster cast, its shape reveals a 165 million year old secret.
One thing that really strikes me actually is the deep impression that this front toe is made and how pointed it is. And this tells me that this dinosaur was moving at a fast speed and really pushing down on its front three toes. So it might have been chasing some kind of prey.
But Megalosaurus wasn't the only dinosaur to leave its footprints in these rocks only 60 miles from Loch Ness.
This is the smallest dinosaur footprint that anybody has ever found in the world. You can actually see it's about the size of my fingernail. And we think it's a coelophysis, and it's quite interesting because the small footprint here, which we think is from a hatchling, is embedded in the larger one here that you can see. What we think this tells us is that the young travelled with their parents in groups, and that most probably the adults were looking after the young.
Geologists have used the amazing evidence of the footprints of Coelophysis and Megalosaurus together with the muddy rocks they were found in to better reveal the story of Loch Ness in the Jurassic period. At the time, Scotland was still attached to America. Plate tectonics had driven this landmass much nearer the equator, 2,000 miles further south than it is now. And that had a major effect on the climate and environment of Loch Ness.
Back during the Jurassic times, the climate and the environment was very, very different to what we see today. There would have been lush jungles full of tropical vegetation, and the dinosaurs would have been living on the edge of these jungles, travelling over lagoonal type of wetlands. This climate was ideal for dinosaurs to live in because it supported a huge ecosystem of wildlife that they would have predated on.
The bones of one more dinosaur have recently been found on the Isle of Skye, the plesiosaur. But this discovery generated a completely different kind of interest. Enthusiasts see a strong resemblance between the shape of the plesiosaur and some descriptions of the Loch Ness monster. Could a descendant of the long-extinct plesiosaur really be the source of the legend? The evidence to unravel the extraordinary geological history of Loch Ness is getting stronger. The findings of Megalosaurus and Coelophysis footprints prove that dinosaurs lived in Scotland 165 million years ago, and that Loch Ness was then a subtropical paradise 2,000 miles further south than it is today. But about 60 million years ago, 5 million years after the dinosaurs became extinct, plate tectonics would tear Loch Ness and America apart. The investigation into how Loch Ness was made now moves forward to a time 60 million years ago. Scotland and America are still firmly joined together. The next question is, when and how did they become separated? On the Isle of Skye, the landscape is full of evidence which can unlock the secrets of this turbulent period in Scotland's past. At Talisker Bay, the massive sea cliffs provide the first clue to the events that devastated the region. They're made entirely of volcanic lava.
I'm standing here on a single lava flow, and this lava flow is only about 10 feet thick. But this whole cliff above me is made up of lava flows, maybe 150 feet or more, and stretching for miles in all directions. Now, these lava flows are composed of basalt. That's the same type of rock that is being erupted today from modern volcanoes like Hawaii or Iceland.
Geologists have calculated that these basalt lavas on Skye are about 60 million years old. But where is the volcano which erupted them? The clue comes from a range of mountains on the southern tip of Skye, the Cuillin Hills. It's the type of rock that makes up these craggy peaks which provide the evidence.
They're made of a rock called gabbro. Now, these are the same chemical composition as the basalt that's been erupted onto the surface, but there's a difference. The basalt that was erupted was cooled very quickly because it was exposed to the air. Geologists call that fine-grained. On the other hand, the magma that was trapped maybe a mile down beneath the Earth's surface, that cooled pretty slowly. It was kept warm for quite a long time. And so you've got very large crystals growing. And when you get a rock with large crystals, that's what we call coarse-grained.
The large crystals in the gabbro rocks give away their origin. They tell geologists that the Cuillin Hills are the remains of an enormous magma chamber deep below the volcano, where lava was stored before being erupted onto the surface. But how much lava was there?
We may be looking now at a beautiful green valley, but actually all these hills around here are made up of rocks that were formed in a series of massive volcanic eruptions about 60 million years ago. And at that time, there were volcanoes erupting all over Scotland. Here we are on Skye, and this is just one of those volcanoes.
It's now known that an incredible 500 cubic miles of lava was erupted on Skye alone. That's enough to cover the whole of Texas with a layer of lava 10 feet thick. But this was just the tip of the iceberg. The rocks themselves reveal that volcanoes erupted all over Scotland on a massive scale. The evidence is here. Huge regular columns in the lava flows, looking like they've been carved out of the rock. In reality, these amazing formations are made by gentle cooling of thick lavas. Exactly the same type of columns are found in outcrops of basalt lava 80 miles away off the west coast of Scotland. And as far away as the coast of Ireland, 150 miles from Skye. These lavas have all been dated at about 60 million years old. And they were also part of the same series of massive eruptions which spread out for hundreds of miles in all directions. But what was the cause of the eruptions? Dr. Goodenough has found another clue which points to the origins of these lavas and their role in the creation of Loch Ness.
This is the ropey top to a lava flow. In Hawaii, they call it pahoehoe. And what happens is that the lava gets a thin skin on its surface as it cools, but it's still flowing underneath that skin. And the thin skin wrinkles and gets pushed forward, giving this ropey texture that we can see here. But it's really quite rare to see them like this in these old lava flows. But it tells us a lot about the type of magma that was erupting from that volcano.
Geologists know that this kind of magma comes from deep within the Earth. It usually erupts on the surface when tectonic forces split the Earth's crust apart. Is that what happened here 60 million years ago?
At that time, Scotland was still joined to North America, but the two continents were being stretched and thinned due to tectonic forces. And that allowed molten rock, or magma, from deep within the Earth to well up and to be erupted from those volcanoes. And eventually, that volcanic activity led to the development of a new ocean between Scotland and North America, the Atlantic Ocean.
So the lavas are the trail of evidence which show that the opening up of the Atlantic Ocean began with volcanic eruptions all over Scotland. As magma erupted under the ocean, the seafloor spread out, slowly pushing Scotland and America apart. The birth of the Atlantic Ocean had a direct effect on the making of Loch Ness. As the ocean grew, the huge forces involved reawakened the 400-million-year-old Great Glen Fault.
So faults like the Great Glen, these are zones of weakness in Earth's crust. And they're like scars or wounds. They can reopen. And in the case of the Great Glen, it was reactivated when the Atlantic began opening 50 to 60 million years ago. And this is why you see this feature now present in today's landscape, even though the fault itself is 400 million years old.
The massive geological movements shattered and weakened the rocks along the fault. Along this line of weakness, a river started cutting down through the shattered rocks, slowly carving out a valley. For the next 55 million years, the landscape of Scotland weathered and eroded. The outlines of the mountains softened, and the coastline began to take on its present shape. Loch Ness became a long river valley, following the line of the Great Glen Fault. The investigation is close to uncovering the final stages in the story of how Loch Ness was made. Huge lava flows on the Isle of Skye reveal that massive volcanic eruptions 60 million years ago were the start of the separation of Scotland and America. The sharp outline of the 400-million-year-old Great Glen Fault shows that the fault was reawakened as Scotland and America were torn apart. But there was one final land-changing event to come. Nature wasn't finished with Loch Ness, and it was this event that created the lake we see today. Tracing a violent history that lasted for 3 billion years, the investigation into how Loch Ness was made now moves forward to the recent past, only 10,000 years ago. The final link in the chain of evidence is to discover how the wide, deep waters of Loch Ness were finally made, and whether a descendant of the dinosaurs could possibly have survived there to create the myth of the Loch Ness Monster. A vital clue was uncovered in the 19th century by one of the greatest scientific minds the world has ever known, Charles Darwin. In 1838, Darwin came to Scotland to investigate a mystery in the remote valley of Glen Roy, about 20 miles from Loch Ness. For hundreds of years, people had been baffled by 3 extraordinary parallel lines which run round both sides of the valley. Strange horizontal cuts in the hillside, in some places more than 30 feet wide. These parallel roads, as they are called, run exactly level for more than 20 miles. What could have made them? Dr. Pete Nino is following in Darwin's footsteps to the Glenroy parallel roads and the story they reveal.
Their creation was a mystery for a very long time, and initially people just thought they were perhaps created by giants, a thing of myth or legend. And then in the 19th century, a number of scientists came here, including Charles Darwin. And when he saw them, he thought they were exactly the same as features he'd seen in South America, where earthquakes had uplifted old marine shorelines and left them abandoned higher up from the sea.
Darwin was so convinced the parallel roads were the remains of old seashores that he published a paper with his results, and the world of science believed him. But for once, Darwin was wrong. In 1840, 2 years after Darwin's visit, a Swiss scientist named Louis Agassiz came to Glenroy. Agassiz had spent a lifetime studying glaciers and the effects of glaciation on the landscape of the Swiss Alps. When he examined the parallel roads, Agassiz realized that they were ancient shorelines, but that the valley had been filled not by the sea, but by a freshwater lake. From his knowledge of glaciers in the Alps, Agassiz was able to show that a freshwater lake had once filled the valley. The lake was kept full by a huge glacier which blocked the end of the valley. As the glacier melted and froze again 3 times, the water in the valley emptied and filled up to a different level, carving out the 3 relic beaches.
Initially, Agassiz wasn't believed because people believed Darwin, and then over time it became clear that Agassiz was correct, and Darwin claimed it was one of his great embarrassments that he'd got something so terribly wrong, which sort of shows that even great scientists can make mistakes.
The evidence at Glenroy convinced Agassiz that many features in the Scottish landscape must have been made by glaciers. And that led him to the startling conclusion at the time that the whole of Scotland had once been covered by ice.
And the moment you make that leap that what you've got here was created by glaciers, you've instantly got to make the leap to the fact that we must have had a very cold climate here in the past, cold enough for ice sheets and glaciers to build up. This site is of world importance in terms of the understanding of glaciations and the fact that in the past ice covered a much larger proportion of the planet than it currently covers.
This extraordinary investigation led eventually to the idea of the Ice Age, periods in the geological past when much of the northern hemisphere was covered in glaciers and ice sheets. Since Agassiz's discoveries, scientists have been investigating the role of ice in making Loch Ness.
About 2.5 million years ago, the global climate started to cool, and since then we've had a series of repeated glaciations, roughly about once every 100,000 years.
Each time the ice advanced, temperatures plummeted. Average winter temperatures were at least 30 degrees colder than today. As the ice built up, it reached extraordinary thicknesses.
The ice sheet over the centre of Scotland would have been 3,000 or 4,000 feet thick. Here in Loch Ness, it would have certainly been a couple of thousand feet thick. You might have seen a few of the highest mountains just peeking out the top of the ice sheet, but in the main, the whole of the landscape would have just been blanketed by ice.
But what effect did this vast weight of ice have on the creation of Loch Ness? The loch itself is difficult to investigate because it's full of water. But there's another location where the evidence is clear. Just 20 miles from Loch Ness is the forbidding valley of Glencoe. Glencoe is a legendary place in Scottish history, as it was here that an infamous massacre took place in 1692, when the MacDonald clan were murdered in their beds by the Campbells. The shape of this valley sheds light on the way Loch Ness was made.
If you could actually drain the water out of Loch Ness, what you'd actually end up with is a valley with this sort of shape. And looking down Glencoe, you can see it's a very, very steep-sided, flat-bottom valley, and it's basically been created by glaciers repeatedly flowing down the valley, eroding it, and basically gouging out what was originally a V-shaped valley and turning it into an over-deepened U-shaped valley.
Glaciers are extremely efficient at eroding the landscape. they pick up vast amounts of rock debris, which is carried along at the base of the glacier. With the weight of millions of tons of ice on top of it, this rock debris grinds away the bedrock like sandpaper, scouring and deepening the valleys to a characteristic U-shape. Across Scotland, there are hundreds of valleys with this distinctive U-shape, bearing witness to the huge number of glaciers which once covered this whole region. At Loch Ness, underwater mapping has revealed that the loch has this signature U-shape. It's flat-bottomed with very steep sides. In some places, only 50 feet from the shoreline, the water is over 500 feet deep. Further proof that Loch Ness was made by a glacier. There was already a long river valley which had formed along the line of weakness created by the shattered rocks along the Great Glen Fault. Then, during the last ice age, a giant glacier flowed down the valley, slowly carving out Loch Ness.
As ice flows down it, it scours it out, deepens it, and over a series of glaciations, it deepens it to the extent that it's now, a loch 750 feet deep.
The investigation is now faced with two final questions. How did Loch Ness fill up with fresh water, and what keeps it full? Loose rock and boulders found on a huge ridge 250 feet high at the head of the loch could provide the answer.
The immediately obvious thing about these large rocks is that they're extremely smooth and well-rounded, and that indicates that they've been transported by water. They're also very large, this is very heavy, so you need a lot of energy, so that tells you that you've got a lot of meltwater that's carried it and then subsequently dumped it where we are now.
This evidence, combined with discoveries about climate change, shows what happened here. About 10,000 years ago, global temperatures rose rapidly, the ice began to melt, and the glaciers retreated.
Glaciers down there would have been eroding Loch Ness, bringing up large amounts of sediment, and that sediment is then being transported in this direction by the flowing ice and also by flowing meltwater.
As the ice melted, a huge river formed under the Loch Ness Glacier, carrying with it vast amounts of rock debris.
And then what we've got here, what we're standing on, is in effect the zone where the glacier is now dumping that sediment.
Millions of tons of rocks created an enormous plug which dammed the river and stopped the water from escaping. As the ice melted, the valley filled up, finally making the lake we know as Loch Ness. Loch Ness is only 10,000 years old, but the investigation into its history has revealed an amazing story. Old red sandstone rocks show that Scotland and the US were once joined together. The shape of Loch Ness is controlled by the Great Glen Fault, formed when Scotland and America crashed into England more than 400 million years ago. Fossilized dinosaur footprints place Loch Ness near the equator during the Jurassic period. Lava flows reveal that massive volcanic eruptions 60 million years ago began the separation of Scotland and America. And the profile of Loch Ness proves that it was carved out by glaciers 10,000 years ago, finally creating the Loch Ness we know today. But what of the Loch Ness monster? The iconic image is now known to be a fake. But is there any way that the mythical beast could be a descendant of the dinosaurs?
We have two geological facts that tell us that Loch Ness cannot be inhabited by a dinosaur. One is the dinosaurs died a long, long, long time ago, and the loch itself, geologically, is very young. Dinosaurs went extinct 65 million years ago. So 65 million years to 10,000 years, it's a long time distance, and there is no chance at all that you would have preserved in this loch an ancient monster from times millions of years ago. The loch's too young.
So the geological evidence proves that Loch Ness could not be home to a dinosaur that somehow survived there since the Jurassic. The awesome geological history of Loch Ness has thrown up many mysteries. But for science, the The Loch Ness Monster is not one of them.